Hello everybody, let us now continue our discussion. So in the last lecture we were talking about the characterization of polymorphs via single crystal XRD and powder XRD, and now we will look at some of the remaining techniques which are useful for characterization of polymorphs. So the next technique is spectroscopic techniques, where we look at IR or Raman as well as solid state NMR. I will give you a very brief overview of how these techniques are useful. For example, let us consider a CHO hydrogen bond which is participating in an interaction with a carbonyl group. Now what happens is that when you have strong hydrogen bonding between the hydrogen and the oxygen, the CO bond tends to weaken. The CO bond tends to weaken because some of the electron density which is available on oxygen now participates in hydrogen bonding with the hydrogen atom because of its electrostatic character, and there is some polarization of the electron density from the CO double bond towards the oxygen atom, as a result of which the carbonyl stretching frequency is now lowered. The stretching frequency is lowered, and because of which we see that this decrease in the stretching frequency of CO, this process is referred to as a red shift, in the sense that the energy which is necessary to stretch the CO bond is now reduced. Now the CHO hydrogen bond is thus a very important signature in the IR spectrum of the compound which participates in this interaction. So when we tend to have strong hydrogen bonding, there is a weakening of some functional the stretching frequency of some functional groups, and that is reflected in the nature of the environment in which these interactions are present with corresponding changes in the IR spectrum. Raman is also complementary to IR, and Raman spectroscopy can also be performed, and it has been observed that for both IR and Raman, the spectroscopic signature in the solid state for different polymorphs is going to be different. By and large, the skeletal vibrations, those involving the CC bonds, CH bonds, these things remain the same, but it is the polar functional groups are the ones that participate in hydrogen bond formation either as a donor or as an acceptor, which are affected by the hydrogen bonds, and the stretching frequencies of these donors and acceptors get affected. Solid state NMR is also another very important technique where we look at the local structure, and particularly in the case of polymorphs, because the arrangement is different, the local environment is different, and this gets reflected in the different spectroscopic properties. Different NMR properties get affected because of the variations in the local structure, and its solid state NMR is also very strongly indicative of the presence of disorder in the crystal structure. So if you have, for example, a side chain which is present, so you have got n propyl side chain. The n propyl side chain is continuously rotating in the crystal. Because it is continuously rotating in the crystal, it tends to sample independent conformations. So you have something called a side chain disorder. So this side chain disorder is very common in crystal structures, and because of which the side chain tends to get populated into different orientations, and this is indicative of disorder, and because of which the spectroscopic signature of these carbon atoms in the disordered state is different compared to a propyl chain which is not rotating. So we can look at atomic disorder, side disorder in the crystal structure more closely by solid state NMR, and also in case of polymorphs, the solid state signature is going to be different. The NMR spectrum is going to be different. The next thing we would like to look at is the computational property. So we can now evaluate the lattice energies, and today there are many softwares which are available to compute the lattice energy of a solid. In this case it is an organic solid, And organic solid, the lattice energies tend to be lower compared to that of the inorganic solids. The inorganic solids tend to have very high magnitude of lattice energies. In comparison, organic solids, the range of lattice energies is primarily between 100 to 200 kilojoule per mole. This is the range of lattice energies for organic solids. And in the case of polymorphs, the lattice energies will be different. However, the magnitude of the differences are going to be very small. And the lattice energies can also be partitioned into the E coulombic plus E dispersion contributions, and and here it is this is the electrostatic part, this is the dispersion part. So we can have the coulombic interactions, which also includes the polarization, and this is together called the electrostatics term, and this is the dispersion term. So this together is contributing towards the overall lattice energy of an organic solid. Then we can look at physicochemical properties. For example, different polymers will have different solubility. They will also have different IDR, that is intrinsic dissolution rate is going to be also different for different polymers. IDR is actually the kinetic solubility, whereas the equilibrium solubility the solubility which we measure is actually an equilibrium quantity. So these kind of experiments can also be done, and it has been observed that the initial rate of dissolution of a polymorph is different, whereas the solubility also for different polymorphs is going to be different, but the equilibrium solubility is not much affected. There is not much differences in the equilibrium solubility. The differences are not significant. However, the intrinsic dissolution rate can be significantly different for different polymorphs. So these are some of the very interesting ways in which we can characterize the polymorphs. Now let us look further into the thermodynamics of polymer formation. The thermodynamics of polymer formation. So the relative stability of a polymorph depends on its free energy, G value. We call this the G value, and the most stable polymorph is characterized by the lowest value of G. The most stable polymorph is characterized by the lowest value of G. And so under a particular set of conditions, that is at a given temperature and pressure, the polymorph which has got the lowest Gibbs free energy value is the most stable polymorph, and such a polymorph is referred to as the thermodynamic form, or we can say the thermodynamic polymorph, that is characterized by the lowest value of G under a set of definite conditions of temperature and pressure. Okay. So we refer to this as the thermodynamic form. This is also called the global minima in the energy landscape, whereas the other polymorphs which are formed are called the kinetic ones, are called the kinetic polymorphs. These are also called metastable forms, and they essentially correspond to the local minima in the free energy landscape. So we have got a free energy landscape for the different polymorphs. The one which is the local minima is the kinetic polymorphs, and the interesting thing here is that the kinetic polymorph would always like to convert to the most thermodynamic polymorph, and how fast this process takes place is something which is not defined. It can take place within a few days to few months, and sometimes the kinetic form has got metastability associated with it. It is less stable compared to a thermodynamic polymorph. However, it can still continue to exist for an indefinite period of time in the kinetic form and did not necessarily convert into the thermodynamic form unless you have provided it or given it the necessary activation energy to convert it to the thermodynamic form. Contrary to this, there are some systems, some compounds where the kinetic form tends to slowly convert or over a given period of time into the thermodynamic form as well. So, you can have a kinetic to thermodynamic conversion. And in this regard, it is also very important to keep in mind that crystallization conditions play a very important role. So, you can have kinetic conditions of crystallization. So, when I say kinetic conditions, I mean to say fast rate of evaporation, and then you have kept it at room temperature. You have utilized low boiling solvents which tend to evaporate faster, and you have used provided greater surface area for evaporation. That means the crystallization container has got a much wider surface, so now the rate of evaporation is greater. So, all these are the kinetic conditions of crystallization, and then we have got the thermodynamic conditions of crystallization, where you have slow rate of evaporation, you use high boiling solvents, you do the crystallization preferably at low temperature, that is less than 0 degree centigrade. You can do it between say -5 to 0 degree, or you can also do it between 0 to 4 degree. The idea is to decrease the rate of evaporation of the solvent, so that you are able to get the optimal size crystals. Okay, so so these conditions of crystallization are very important, and it is also necessary to keep in mind that normally the formation of a solid state occurs by crystallization from either the solution or the melt of the compound or from the vapor phase. So, from all these states, that is, you can have a compound which is dissolved in a particular solvent. So, the solution, you are evaporating the solvent, you will get the solid phase. You can melt the compound, take it into the melt, and then allow the melt to crystallize back into the solid state, and it can give the same polymorph, or it might not give the same polymorph depending upon the stability of the polymorphs. And you can also have an organic compound which has gone into the vapor phase, and now you can convert it back from the vapor into the solid state. But our discussion today is primarily focused on thermodynamic considerations which involve transition between polymorphs from solid to solid. So, we are only interested in understanding solid, say S1 polymorph to S2 polymorph, and this is pure phase transition which can occur between two polymorphs S1 to S2 and S1 to S2 or S2 to S1. So, we are more interested in the thermodynamics of understanding interconversion between the polymorphs. As we said, you can have a kinetic form, you can have a thermodynamic form, and kinetic can convert to the thermodynamic, or it can have a certain degree of metastability such that it can exist, the kinetic phase can exist over a long period of time. So, when you consider the relative stability of polymorphs, when you talk about the relative stability of polymorphs, what is important is to consider the rate of transformation of one to the other. And so this the rate of transformation is important. And second thing is the time needed to attain equilibrium. The time needed to attain equilibrium defines the kinetic pathway, but the rate of transformation of one to the other defines the thermodynamic pathway. So what is the time which is necessary to attain equilibrium? Is the kinetic pathway, but the relative stability and the transformation depends upon the thermodynamic pathway. So and here something else plays a very important role. You can actually achieve transformation of one polymorph to another using a solution mediated process. So there is a tendency that when you dissolve a particular polymorph in solution, it will convert into the more stable polymorph assisted by the solution in this or the solvent in which you have dissolved the polymorph, and this solution mediated process plays a very important role. Now let us look at the relationship between the polymorphs in the solid state. So to understand this, we will look at the Gibbs free energy, the quantity the Gibbs free energy G as a function of temperature, and here I have drawn for you the following. So I am first considering a set of polymorphs B, A and C. This is my liquid region, this is my amorphous region. The amorphous phase is characterized by the highest value of G, and the region where the solid line cuts the liquid phase is the melting point of C, this is the melting point of B, and this is the melting point of A. So independently we can see that C is the most stable form, C is the most stable form. It is characterized by the lowest value of G, and B and A are the metastable forms, and the Gibbs free energy value of B is greater than that of A, is greater than that of C, and that of the amorphous phase is going to be the highest. And what is this point? This point is called TT. This is called the transition temperature. When polymorph B, when A converts to B. So you see here, when you start with polymorph A, this is the point at which the G value of B and A are equal to each other, they intersect, and after this the A phase is no longer stable, it is the B phase which is stable, as is characterized by the lower value of G. So A converts to B at the transition temperature, that is characterized by TT. So if you have a transition between two polymorphs B and A below the melting points of the respective polymorphs, in this case respective polymorphs are A and B, TMA and TMB are the melting points, and they actually cut the G value, the free energy isobar. This is the free energy isobar at a fixed pressure. At a fixed pressure you are doing this. This is at a fixed pressure. So this is the free energy isobar. They intersect at A and B. At this point the Gibbs free energy value is equal to each other. So the delta G is equal to 0, and therefore there is a phase transition here. The phase B converts, the phase A converts into B, after which you see that there is a drop in the value of G. So, this is at the transition temperature. This happens before the melting. So, these two polymorphs A and B are enantiotropes. We call this enantiotropes, or the corresponding phase transition is called enantiotropic phase transition. Enantiotropic. Please keep in mind, this is not enantiotopic, which is used for hydrogens in organic molecules to distinguish them in different environments, but this is enantiotropic phase transition. So, in this case A and B are enantiotropes. However, if you were to look at A and C or B and C, if you look at A and C or B and C, they all have got they all exist over the entire range of temperature before they melt at the melting point of TMB and TMC. Therefore, B and C or A and C are monotropes. These are monotropes. So, what is a monotropic pair? So, we have got a monotropic pair, and that is such a pair in which a pair of polymorphs are classified as monotropic if one polymorph is more stable than the other at all the temperatures below the melting point. And A and B are enantiotropes because A converts into B after the phase transition temperature Tt, because after Tt it is the B form which is the most stable, the A form is unstable. Okay. So, there is a thermodynamic tendency for the system to convert to the most stable form, which is characterized by the lower value of G, such that delta G is less than 0 overall for the process. Okay. So, I said delta G is less than 0 for the overall process, then the transformation will happen spontaneously. Okay. So, what happens is that below Tt, A is more stable than B, Ga is less than Gb, so A is stable, but after Tt, Gb is less than Ga, so B is stable. Okay. Below Tt, A is the most stable polymorph, B is the less stable polymorph. So, there is a possibility of a spontaneous exothermic conversion of B to A. So, below Tt, B can undergo a spontaneous exothermic transition to A, and above Tt, A can undergo a spontaneous exothermic transition to B. Now, why this is a very thermodynamically feasible process? Because below the transition temperature, if you start with the B polymorph and keep it for some time, it is still the unstable phase. It is the one which, or it is a metastable phase. So, there is a possibility for it to convert to A by the release of excess G energy, by the release of excess Gibbs free energy, and therefore it will convert into A. So, similarly, after the phase transition temperature, it is the B form which is more stable, and therefore, if you start with A, it will convert into B. So, these kind of thermodynamic processes are well known to take place when you have when you have polymorphs of different stability. So, you can now distinguish from the Gibbs free energy diagram, that is we call this the GT diagrams. From the GT diagrams, you are now able to easily distinguish between whether a pair of polymorphs are enantiotropic related or they are monotropically related. And each particular polymorph exists over a certain range of temperature and pressure. In case of enantiotopes, the stability order is reversed after the phase transition temperature. So, before the phase transition temperature, we saw that A was stable, and after the phase transition temperature, it is the B form which is more stable, because there is a thermodynamic driving force associated with this process, such that it is characterized by a spontaneity in the conversion of A into B, characterized by delta G less than 0. So, if delta G is less than 0, then that particular process is going to happen spontaneously, but if delta G is greater than 0, then that process is not going to take place. So, with this background in mind, we have now looked at different aspects of polymorphism, and now we will look at some examples, a few case studies, so that we are able to appreciate polymorphism better. So, now let us look at this first example, where I will demonstrate to you polymorphism in an anti-implantation agent. This is an anti-implantation agent. This is a keto tetrahydroindole. This is a keto tetrahydro. There are hydrogens here as well as here, tetrahydro, and this is the indole derivative. You can see this is the 5-membered indole ring. This is the nitrogen, this is the phenyl, and this is the fluorophenyl. So, this work dates back to 1980, when this particular compound was used as an anti-implantation agent. And now you can see, when crystallizations have been performed on this particular compound, we have been able to obtain two distinct morphologies, plates as well as blocks. The plates were observed essentially in dichloromethane hexane, and when the crystal structure was determined, these crystallized in the monoclinic crystal system, and the blocks on the other hand, they crystallize from a solution of ethanol and acetone, and these crystallize in the tetragonal crystal system. So, right away you can see that there is a very clear signature of the polymorphism. One is as plates, another is as blocks. It is also realized that crystallizing this compound in different conditions using different kinds of solvents mostly gave the plate form, but the block form was very rarely observed. On determination of the crystal structure and looking at the overall geometry of the molecule, as you can see that that the C9N1 bond and the CC bond is very flexible. There is flexible rotation, and you can see here that the torsions associated with these bonds in the two different forms are different. In one case, this value N1C9 is 58 degree, in another case it is 62 degree, and similarly the N1C9C10 value, this value is 124.6, this is 118, and we can go to the C1C15, again it is different for the two polymorphs. So, this is essentially a signature of conformational polymorphism, where there are differences in conformation associated with the two molecules, with the different molecules in the solid state. Now, let us look at the packing. The packing is going to be very different. This is the plate form. This is the plate form. In the plate form, you can see that there are CHO hydrogen bonds. These are the CHO hydrogen bonds which forms chains, and the chains you can see very clearly are along the C axis. This is the C axis, this is the B axis, and the top is the A axis. So, there is a nice connectivity of CHOC hydrogen bonds. This involves the donor, and this involves the carbonyl group as an acceptor. And another thing, you can see that these chains are parallel to each other. So, one chain is in this direction, another chain is in a parallel direction, and therefore, this arrangement of molecules is non-centrosymmetric. That means there is no center of inversion in the crystal packing. The arrangement of the molecules is non-centrosymmetric forming these kind of chains parallel to the C axis. Contrary to the plate form, the block form, the tetragonal form, the block form, you can see is a very interesting structure, because in the tetragonal form you actually have a four-fold axis in the crystal structure, and here you can clearly see the four-fold axis which relates these 4 molecules which are connected by FF contact. Now, this FF contact which you see is not present in the other polymorph. In the other polymorph, the F fluorines are far away from each other, but in this one the fluorines come together with respect to each other, they come close to each other and form this kind of a cyclic tetramer kind of a thing. And in addition to that, you can also see that there are CH pi dimers here, and okay, there is one dimer here, there is another dimer here, and then these dimers are connected by the CHO hydrogen bonds. Okay, so you have FF contacts which form which bring 4 molecules close to each other, and then you have dimers which are connected by CHO. So we can see this more clearly on the right hand side, where in the plate form you have got the CH pi chains. You see, these are the CH pi chain. This is CH, and this is the pi ring, which is pointing towards the center of gravity of the 5-membered indole ring. So you have got a CH pi contact, you have got a CH pi contact. So this forms a linear CH pi chain, whereas in the other case you have got a CH pi dimer. It is interesting to see that these CH pi's are quite short, and these hydrogens are quite activated because of the presence of the carbonyl group. So these kind of activated CH bonds can participate in the formation of CH pi contacts involving a donor with an appropriate acceptor, because the indole ring is an aromatic system, it has got a lot of pi electron density. So this facilitates the formation of CH pi, and the types of CH pi in the 2 polymorphs are very different. In one case they form chains, in the other case we have CH pi which form dimers. Obviously they involve different types of hydrogen, but the arrangement of the molecules is different. So with this we come to the end of this lecture. Now in the next lecture we will look at more a couple of examples more on polymorphism, and then continue our discussion further. Thank you.